the device characteristics on the constraints of the device. I'll bring this up to make it larger here in a moment. But the load line, coming back here for a second, the load line has linear relationship between VDS and I sub D. When I sub D equals 0, V 0 equals VDS is just V sub S. And when VDS is equal to 0, I sub D is V sub S over RL. So here is that constraint plotted on these characteristics. When I sub D is 0, the circuit constraint says that the output voltage, the drain to source voltage, is just equal to V sub S, and that is that intercept on the curve, on the characteristics. When VDS equals V sub O is 0, the circuit constraint says that the current is equal to V sub S over RL, and that is that point on the current axis. Then I've simply drawn a straight line, the linear relationship, the load line relationship between those two intercepts, and that load line now enables us to calculate the output voltage, which is the drain to source voltage, for any value of VGS. For example, the threshold voltage in this transistor is somewhere down here below 3 volts. So if I were to say what is the drain to source voltage, the output voltage, for a gate to source voltage of, say, 2 volts, an input voltage of 2 volts, because the gate to source voltage is indeed the input. When V sub I is 2, then V sub O is just 8. Line now enables us to calculate the output voltage, which is the drain to source voltage, for any value of VGS. For example, the threshold voltage in this transistor is somewhere down here below 3 volts. So if I were to say what is the drain to source voltage, the output voltage, for a gate to source voltage of, say, 2 volts, an input voltage of 2 volts, because the gate to source voltage is indeed the input. When V sub I is 2, then V sub O is just 8. And this then can be done by following right up along the line for each intersection of a transistor characteristic curve with the load line. There is a particular value of VGS and correspondingly a particular value of I sub D. We're plotting VGS equals V0. So if I go up here to 3 volts and look, eyeballing that says that the drain to source voltage is about 7.4 volts for 3 volts on the input. This is about 7.4 volts. And if I go up to 4 volts on the input, it's about 6.5 volts, maybe 6.5 volts is about as close as you can call it. And so on, for every intersection, till finally I get over here at VGS equals 10 volts. And at VGS equals 10 volts, it looks to me like the drain to source voltage, the output voltage, is about 1.5 volts. Now, rather than do this in a ponderous kind of way, let me just put down these other values. At 5 volts, it's 4.3. You can check these yourself if you'd like. At 6 volts, it's 2.9. At 7 volts, 2.2 volts. At 8, 1.9. And at 9, 1.7. So putting the load line on the characteristics of the transistor enables us to calculate, to determine, to express the relationship between the input voltage, which is the gate to source voltage, and the output voltage, V sub O. Back at the complete model, we've now got a tabular relationship between V sub O and V sub I. I should be clear here that there is no curve for 2 volts, and I'm assuming that the threshold voltage is somewhere below 2 volts. so that at 2 volts the thing is not conducting and we are at this point on the load line. Now this relationship, this tabular relationship, can be plotted, and plotting it gives us what is referred to as the transfer characteristic. No need to pay attention to the details here, but this is the output voltage, V sub O. This is the input voltage, V sub I. The numbers by the tick marks are voltages in volts. And the transfer characteristic that results from plotting that table on the previous graph, that is, if I plot these data over here at the left, which I generated by looking at the intersections of the load line and the transistor curves, plot those, this is what comes up, the transfer characteristic of the device. Nonlinear, but clearly V sub O is being controlled by V sub I. And for our purposes at this time in the subject, this control is being exercised with the expenditure of no energy. That is, the drain current is 0. So you can control the the gate current is 0. You can control the gate to source voltage with no expenditure of power at the gate to source terminals, 0 current. Here we are controlling the voltage across the resistor, the load resistor, and that is clearly dissipating power in the load resistor. This is the same characteristic. Let me blow it up just a little more. I'll cover up the larger, the definitions of the voltages, same curve. And I've kind of arbitrarily in one respect, characterized this as 3 different regions. There is the region between these 2 lines where the nonlinearity is pronounced, and I'll refer to that as the active region. The MOSFET is the first active device we're going to study. And for this circuit, with this device, this is the active region, where there is a strong dependence of output on input. I've referred to this as the cutoff region because for V sub I less than 2 volts, indeed the transistor is cut off. In switch terms, it is in the off state, and so there's no dependence of the output voltage on the input voltage. And then as we go to higher and higher input voltages, this curve kind of tails off with not much slope, and I've referred to that as the saturation region. That is, the gate to source voltage, the output voltage, is saturating at some level in the range of a volt or 2. In the active region, the device can be thought of is an amplifier. How can we describe the gain of the amplifier, the voltage gain of the amplifier, under some conditions, under some limited conditions within the active region? Well, the incremental or the small signal gain is related to the slope of this transfer characteristic. And at this point, I'm differentiating between total variables, V sub O, V sub capital O, and V sub I, V sub capital I, total variables, and incremental or small signal variables. In other words, what I'm going to do is pick an operating point somewhere in this active region. Let's pick the operating point right here. There's an operating point which corresponds to a value of the input voltage of 5 volts. Get that a little bigger here for you. And it produces a corresponding output voltage of a little over 4 volts. Let me look back at my table. 4.3 volts. This operating point here then is described by the coordinates 5 and 4.3. And if we look at the slope of this transfer characteristic at that operating point, that slope is to first order a measure of the incremental or small signal voltage gain of this circuit at that operating point. Now, in order to be clear about the distinctions between total variables and incremental variables, what we're going to do from now on is write V sub O, the total output voltage, is equal to capital V sub capital O plus little v sub little o, and the total input voltage, V sub I, is equal to capital V sub I plus little v sub little I. These variables, these are operating point values. And these variables are incremental or small signal variables. Here, and operating point values here. So if I want to know the relationship between little v sub I and little v sub O, it corresponds to the slope of the transfer characteristic at the particular operating point. The operating point defined by 5 volts for capital V sub capital I. Clearly, if I pick a different value, if I go to 6 volts, I'm here, the slope is less. Slope is negative in any case through this region, but the slope is less here, lower incremental voltage gain. If I pick one up here at 3 volts, the slope is also lower. I've intentionally chosen 5 because it's, as best I can tell on this crude diagram, it is the point at which the slope is greatest. Now I've chosen this operating point in an effort to put it at the point on the transfer characteristic where the negative slope was largest. That's at the 5 volt input operating point voltage, capital V sub capital I, and I've drawn a tangent at that point and then extended it out in an effort to get a reasonable measure of the slope of that tangent. So I extended the tangent out to the 4 and 6 volt lines, and it's a 2 volt difference here on the horizontal axis, and the corresponding intercepts on the vertical axis are at a little over 2 volts and a little over 6 volts, and the difference is 4.2 volts. That comes from the table we drew previously. Now that 2 volts horizontally, 4.2 volts vertically. The tangent is the straight line here. It re-intersects the curve up here because of the shape of it, but don't be put off by that. It's an effort to make a tangent at this point. If we take that ratio of 4.2 to 2.1, and it's a negative number, this slope is negative, or 2.1, this is equal to, before I do that, let's say put the units on it. This is 2.1 volts per volt. This is the incremental voltage gain minus a negative quantity, or equivalently the small signal voltage gain.
That's it?
That's it.
Could you just do a wrap-up with you on screen?
So the ratio of the vertical height to the vertical intercepts to the horizontal intercepts of the tangent is the small signal voltage gain, the incremental voltage gain of this device. Our purpose was to classify or to characterize in some way how the device behaved as an amplifier, and this is a description for operation around that operating point with signals small enough so that the linear approximation is a reasonable one.